Okay, so u would be negative because it is in front of the lens, and here this is minus x as this is positive x as is. So u would be here, so u will be negative. F is real, and so it will be here. V, the image form is real, and so it will be here. It will be here. So V will be positive. Please, are we okay with this?
Procedure, please. Is that for the NC conversion?
Yes. Just because here we are plotting, okay, not calculation, because for calculation we realize it will not work. But because we are plotting on a Cartesian plane, that is why we are making this consideration. So if you attach these signs to it, this is positive. 1 over V is positive. U would be also a positive because negative, negative. So this will be positive. And then F will be minus. Please, are you okay with this? So when you plot,
Mr. Please, you said what to be minus.
okay, let me, after explaining this, let me still maintain this and then substitute the values in. F is negative, so this is minus. Okay, then U is negative, this is minus. Then V is positive, still it stands. So because I'm plotting 1 over V against 1 over U, I have to make 1 over V the subject. 1 over V will be equal to 1 over U, okay, minus 1 on F. 1 over U is negative. When it crosses, it will be positive. That's why we have this. Okay, minus 1 over F. And this will conform to equation of a straight line. 1 over V is Y. So Y is equal to mx. Here our x is 1 over U, okay, plus C. Our C is 1 on F. So when you plot this, you see the gradient is positive. M is positive. M is equal to 1. Okay, so it will be a positive graph. Look on the graph. It will be a graph like this with a positive slope, cutting the vertical axis. The intercept on the y-axis is this. So this will be the equation of the line where our y is 1 over V, our u is our x is 1 on U, and then the intercept C is, this is where the line cuts the vertical axis C. So from here we realize that the intercept C is equal to negative 1 on F. Okay, so in practicals, what we usually do is that you can use this to find the focal length of the lens. When you have determined where the line or the graph cuts the vertical axis, assuming on the graph this is 10. This is 10 centimeter. Where the intercept on the vertical axis, this is 10 centimeter. It means that C is 10, okay, which is equal to 1 on F. So when you find F, when you make F the subject, F will be equal to 1 over 10, telling you that the focal length of this lens we use for the particle is equal to 0.1 centimeter. So by the graph, when you determine the intercept on the vertical axis, you can easily find the focal length of the lens used. So, hello.
Please, I was a bit confused.
All right, I'll go over. You see, let me quickly go over for the last time. You were given U. So we found U, we found V, and plotted 1 over U against 1 over V. Okay, the instruction is that we are to plot a graph of 1 on V against 1 on U. All that we are doing, the intention or the thoughts behind this is to use this method to find the focal length of the lens. So we are plotting this. The vertical axis is 1 over V. The horizontal axis is 1 over U. Okay. Now, because we are plotting this on a graph, we are going to use the NC convention to determine the value of. So using the equation of a lens, 1 on F on 1 on U plus 1 on V. Okay. If the image form is real, and here is a real image because we captured the image on a screen, then it means that per the position, this is the lens, per the position of the object, we are saying U is a negative because U would be in front of the lens. F would also be a negative, but the image is real, meaning it will be the other side of the lens. So V will be positive. Come and substitute this signs into the equation. This is negative. Okay. Then U is also a negative. V is a positive. But you see, because we are plotting 1 over V against 1 on U, it's similar to equation of a straight line. Y is equal to mx plus c. Okay, so we have to make 1 over V the subject. So it means 1 on U has to go to the other end. So we have 1 over V is equal to positive 1 on U minus 1 on F. Please, are you okay with this equation? Meaning that this is my V, this is my X. M is actually equal to 1. Okay, M will be equal to 1, and C is equal to this. So if I'm plotting this graph, it means that the intercept is negative because there is a negative here. And because the gradient M is equal to 1, it will be a positive graph. Positive graph always is like this. Negative graph is the other way around. So if we had the gradient to be a negative, then it would have gone this way. Okay. Here the gradient is positive, so it will be a positive graph. But where does the graph cut the vertical axis? When you plot it, this is how it goes. Okay. The graph cuts the vertical axis at negative. So this is C. Okay. Then when you compare this to equation of a straight line, you realize that the intercept on the vertical axis, C, is equal to 1 on F. Meaning that you can read C on a graph, and C is the intercept on the vertical axis. You can read that from the graph. So from your plotting, if you know the value of C, the intercept on the vertical axis, you can easily use that to find the focal length of the lens. So I'm assuming,
Please, is there 1 on F or minus 1 on F?
Oh, we are taking the magnitude. So the minus is not really a situation, but we are only considering the magnitude. Okay.
Okay.
So in essence, it's actually 1 on C is equal to, or 1 on F is equal to negative C, because this is okay. But when you consider the magnitude, you just ignore the sign. So when you If you have C, if you have the intercept on the vertical axis, then you can easily determine the focal length of the lens. So the concept to be learned is that whenever you plot a graph of 1 over V against 1 on U, the intercept on the vertical axis is always equal to C is always equal to 1 over the focal length. So when you make F the subject and then you substitute whatever you got for C, you have found the focal length of the lens. Okay, this is something you understand better when we conduct practicals and plots. Then I ask you to find this. Okay, so this is the theory. When we do the practicals, you understand what it means. But what you have to learn is that when you plot a graph of 1 over V against 1 on U, okay, the intercept on the vertical axis C is always equal to 1 on F. So when you compare this equation, 1 over V, blah, 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 to equation of a straight line, 1 y is equal to mx plus c, the intercept would always help you find the focal length of the lens used for the practicals. Please, are we okay? Are we fine?
Please. Yes, please.
All right. So the next method of determining focal length is the method of displacement. Let's quickly go through it because, in fact, I'm bent on finishing, even though we'll be left with optical instruments, which we'll do in school. But let's quickly go through this and then the method of displacement. Under the method of displacement, what we do is that the distance between the objects and the screen is kept fixed. So we have the lens is here, the screen is here, object is here. This distance between the screen and the object, represented by the letter D, is always fixed. We don't touch it. We don't touch the distance between the screen my markers are a failure. So D, which is this whole distance, we don't touch it. Of course, from the object to the lens is the object distance, U. If this is U, when we subtract U from D, D minus U, this gives us V, the image distance. Are we okay? So the image distance is D minus U, which is this. Now, under the method of displacement, this distance between the object and then the screen is kept constant, but the variation is always, you hold the lens and then vary. Let me put the lens in the holder. Hey, Hilda, are you there? Hilda, one.
Yes, please. Mr. D,
Oh.
I'm here.
Okay, it's been a while. Like Nana didn't find it again. So the lens is in a holder. So you see, in the first one, we were adjusting the screen to get a sharp image. For this method of displacement, we don't touch the screen, but we adjust we adjust the lens to get a sharp image of the object on the screen. And this can still be the illuminated objects. Are we okay? Now, what you have to learn here is that, you see, the method of displacement can give you two different positions. Okay. There can be possible two positions for image formation on the screen. Okay. So practically when you move it, when you bring it closer to the object, you can have an image captured on the screen. Then you measure U and then find V. I said this is fixed. So the moment, when assuming you are given this to be X, if I adjust this and I get a very sharp image, it means the distance from here to where I place the lens is U. Once I have U, because I know this, I would have to subtract U from D and I get V. And you plot it on the, okay. Now, if you adjust it again, when it comes closer to the screen, it can possibly give you another position of image. You can get another position where you can record a very sharp image again of the object on the screen. So for the method of displacement, usually for different positions, you can get two different positions for a clearer image on the screen. Unlike the first one where you had only one. Here, depending on the position of the lens, you can have two different positions, okay, on the principal axis where a clearer or sharper image can be formed on the screen. Now, the conditions pertaining to this is that if you have D, displacement, the displacement between the object and the screen being equal to 2 times the focal length, you only have one position for a clearer image, one position for a clear image. Example, let's assume the focal length of this lens is 20 centimeters. It means D is equal to 20 times 20, which is 40. So if the distance between the object and the screen is 2 times the focal length, then this relation would always give you one position of clearer image. I'm assuming that the focal length of the lens is 20. If you have D to be equal to 2 times 4 times F, 4 times F, 4 times the focal length, okay, example, I say equal to greater than 4 times the focal length. You always have two different positions for a clearer image, meaning that when you bring this here, you can have an image formed on the screen. When you adjust it and bring it closer to you, also have another one. But this is on condition that the displacement D must be greater than 4 times F. You understand this better in practicals. For now, it may sound confusing, but let's just look at the theory. When you apply it, I think I'll help you go through the practicals and you understand these conditions I'm talking about. Is that okay? So here too, example, assuming the focal length of the lens is 20, meaning we have 4 times 20, giving you 80 centimeters. What this means is that if you have D, the displacement between the object and the screen, and then the D value is anything greater than 80, you have two different positions for formation of clearer image on the screen. Okay. Now, any measurement when D is less than 4F, no image will be formed. Okay, so you love it. Let's pause here. I think you understand this thing better in practical. So just let's go through the theory as we have. When school reopens, I'll find time, go through this practical thing with you, and your understanding of the concept will be better. Okay. So class, this is where if you have any question, quickly ask. If you don't have any question, let's end the class here and then continue it on Friday. Friday, we are moving on to a new area, either simple harmonic motion or circular motion or wave motion, one of them. And I'm sure we'll look at SHM. Okay. So if you don't have any question, please, this is where I draw the curtains on today's meeting. Thanks for your presence. Please revise. If you have any questions, send it to me on WhatsApp. I can explain for you. Until then, bye-bye. Take care of yourself. Please, my roll call, if you haven't acknowledged your presence, quickly do that for me. Okay. Bye-bye and good night to each one of you.
Bye bye.